very good. So I'll mostly, well, almost exclusively talk about Michaelis-Menten indeed. And this is an old and in a way an odd topic because I thought I had graduated from that a long time ago, but then I came back to it. And there is a qualitative matter to that, which is really, there's nothing to say about that, but there's also a quantitative matter. And that's what I started to work on again. I'm trying to give this talk, well, in a gentle way and also include a few hopefully helpful hints on literature, etc. In the end, the slides will also be on the MoRN webpage. Good. I should say that this is about joint work in progress with Justin Eilertson and Santiago Schnell. And I should say something about terminology. Small parameter, that's a weird way of stating things. That's a parameter that needs to be small for some desired behavior, like reduction of dimension to occur. Okay, so Michaelis-Menten. This is probably known to everybody. So here we have substrate and enzyme combining reversible to complex. Complex may also degrade irreversibly to enzyme plus product. With mass action and stoichiometry, one gets this well-known system of two differential equations. Now, yeah, there are reductions, and there is a classical reduction by Briggs and Haldane, asserting or assuming quasi-steady state for complex. That means C dot should be very close to zero. If you assume it's really zero, you just solve that right-hand side here for C, and you get the quasi-steady state manifold. Plugging that in, you get the Michaelis-Menten equation. I think that's really known to everybody. There's a reduction for small k2 when the production of product is actually very slow. That was what I think was really the goal of Michaelis-Menten, and I'll need to talk about that later. Good. So when one thinks of practitioners, people in the lab, they think, okay, I would like to have a certain parameter which guarantees that the reduction works. And so my working definition, I'm not sure I understand that correctly, by the way. A small parameter is some combination of reaction parameters, such that, first of all, it is controllable by experimental setting. It is dimensionless, and delta very much smaller than 1 ensures the desired behavior, like approximation of the full 2D system by the Michaelis-Menten equation. And ideally, one would like to have some uniqueness. I've learned that this much less than sign is really the most enigmatic relation in all of mathematics. It seems to have many interpretations, and it may not always be used properly. So one of my goals was, okay, really get rid of that, or at least give it a concrete interpretation. Now, small parameters in the sense just mentioned, when enzyme concentration is low. Briggs and Haldane really introduced initial enzyme concentration by initial substrate concentration. Heineken and co-authors used that as a basis for the first singular perturbation, proper singular perturbation reduction. Reich and Selkov used this parameter, K1 is 0 by K negative 1 plus K2. So that's something like production of complex over degradation of complex. And then there's the famous Siegel and Slemrod parameter. K1 is 0, and then there's still a term that's S0 here in the denominator. So what can be said about those parameters? The Heineken parameter and the Siegel and Slemrod parameter seem to open up an interesting possibility. Just add more substrate, and you will always get quasi-steady state, according to that. Actually, that cannot be true for not only for chemical reasons, but also for mathematical reasons. So there is something problematic about that. Reich and Selkov seems to be okay in that respect and will turn out to be really okay. So testing Siegel and Slemrod. This is a simulation On the left, you see some piece of the phase portrait in red. That's the quasi-steady state manifold. On the right, you see the same thing, but now with time over a smaller range. And one sees here S0 is large, the rest not so. The Siegel-Slemrod epsilon is about 10 to the negative 2, which might be qualify as much smaller than 1. The solid black curves are trajectories. And here on the left, you see, okay, as long as there is sufficient substrate, you're getting a very good approximation to the of trajectories to this quasi-steady state manifold. If you look at it closer, well, when there is less substrate there, then there is a notable discrepancy. So, and even more than that, we noted that when we did a few experiments, well, numerical experiments, looking at trajectories alone is not a good idea. So on the left here, you have a very close setting, very close to the stationary point 0. Red, if you can still identify that, is the quasi-steady state manifold. Black is still trajectories, which very quickly turn to that quasi-steady state manifold and then remain on it. But if you look at the evolution of substrate in that case, with time, you see that the proper solution, which is here in solid black, definitely is different from what the reduced equation seems to tell you. So one should not only look at those phase portraits, one has to look at time dependencies too. So we noticed that, and yeah, so we're trying to accommodate that. Now, let me get to the theoretical underpinnings of the whole thing. Singular perturbations. That's not the whole story for chemical reaction networks and reduction, but it's a very big part and important part of the story. I'll restrict myself to that. And also, just to avoid writing down lots of things, I restrict myself to 2D, dimension 2. So here we have a singularly perturbed smooth system in Tikhonov standard form. On the left, it is in fast time. On the right, it is in slow time. What is typical, there is a slower part, here the first equation, and there is a faster part, here the second equation. If you rewrite that in slow time, you see that the epsilon turns up at the left-hand side here. At epsilon equals 0, you're getting an algebraic equation, actually. F2 equals 0. And it's natural to think, okay, why not solve this algebraic equation for x1 as a function of x2, plug that in the first equation, and have a reduction to dimension 1. Now, the theorem, due to Tikhonov and later Fenichel, in a much more general setting, tells you, okay, you're allowed to do just that given certain natural conditions. So you need a point x star so that F2 vanishes at x star when epsilon is equal to 0. And then the partial derivative of F2 with respect to x2 should be negative. Then first of all, that's implicit function theorem. For sufficiently small epsilon, there exists a local resolution. So F2 equals 0 exactly if x2 is a function g of x1 and epsilon. And this approximates a local slow manifold up to errors of order higher than epsilon. For epsilon equals 0, one calls the thing critical manifold. The slow manifold is locally exponentially attracting, and as epsilon turns to 0, one really gets, okay, convergence of the system, solutions of the system in slow time to solutions of this reduced equation. Just express x2 as a function of x1, plug in. So that's, in a nutshell, the Tikhonov-Fenichel theorem here. Let's look at an example, Michaelis-Menten, with slow product formation. I should say here, slow product formation is not the most popular of the Michaelis-Menten cases, but for me, it's technically easier. Not at the moment, but it will be later. Okay, one needs to introduce an epsilon there, and the epsilon was not there at the beginning, so I smuggle it in here. Slow product formation means small k2, so let's call that epsilon times k2 star, some reference value k2 star. This system is not yet in standard form, but one can rewrite it easily to put it into standard form. Let x1 be total substrate, S plus C, and x2 be equal to S. And then you get this equation, x1 dot. Okay, now in Tikhonov standard form, you can read it off yourself. And I did some high school algebra. The critical manifold here has the form x2 is gx1, reduced equation, okay, just according to recipe from Tikhonov's theory. So that's down here. Now, there are small parameters. I showed you some at the beginning, and naturally those small parameters were obtained with a bit more than just guessing. At least it was educated guessing. So what can one generally say? One starts with a parameter-dependent system. X dot equals hx pi. Pi stands for parameters here. Sorry for that strange notation. And the pi's are, okay, reaction rate parameters and so on. From first, a priori, there is no epsilon there. So, and one needs to identify conditions for some relevant parameter to be small. And there are some strategies here. The classical one by Heineken and co-authors is to scale. One way to do that would be, okay, E0 should be small, so let's call it epsilon E0 star, and then scale C along with it. And this would enforce Tikhonov standard form onto the system. Siegel and Slemrod went to a different path. They said, okay, here we think of the system having two time scale regimes, identify those time scale regimes and compare them. Okay, the two time scales then, okay, one should be much smaller than the other. Lamb and Gussis, mostly working really on engineering problems, combustion and so on, they used timescales via eigenvalues of the linearization. In dimension 2, the matter is really, for, if you have real eigenvalues, I should say, you have the timescales, okay, these are the inverse absolute values of the eigenvalues, and timescale ratio is the important thing, in case both eigenvalues have the same sign. One needs to handle that with care. I'll get back to that in a moment. And I should note that a recent paper by Patsatsis and Gussis gives a very extensive discussion of Michaelis-Menten via eigenvalue ratios and via computational singular perturbation theory. This is also from one could say from an engineering perspective. So now again, what about those strategies? The classical one, Heineken, has the problem that there is always some artwork, I call it, necessary. And there is a problematic parameter, as I mentioned before, E0 by S0 can't be the whole story. Identifying and comparing timescales the way Siegel and Slemrod did, though there is a problem that involves a heuristic notion of nonlinear timescale, and also remember the problematic parameter. Lamb and Gussis, okay, timescales via eigenvalues of linearization. This is, first of all, a consistent notion, and second, it's mathematically solid, as Tsagaris, Karpa, and Karpa showed some time ago. But, and that's the handle with care part, one needs to restrict that to neighborhoods of stationary points. Far from stationary points, one should not look at eigenvalue ratios or stuff like that. So, yeah, and then there's the other theoretical thing I need to talk about. There is a sort of algebraic approach to this finding of small parameters. And the idea was not to look at the epsilon, but rather to look where epsilon equals 0 could lie. So that's Alexandra Göke's doctoral dissertation and some ensuing publications. So what happens with a system in Tikhonov standard form at epsilon equals 0? Okay, you see x1 dot equals 0, and that means under sensible conditions, the system at epsilon equals 0 admits in our case, we are in dimension 2, a curve of stationary points, non-isolated stationary points anyway. So if you have a general parameter-dependent system, look for a parameter value pi hat, so that hx pi hat has non-isolated stationary points. That's a problem with serious algebraic flavor, in particular when h is polynomial or rational. Then fix pi hat and choose a curve in parameter space. Now here comes in the epsilon. Pi equals pi hat plus epsilon rho. Rho is some ray direction in parameter space. And this gives you x dot equals, okay, something which now looks like Tikhonov-like. Okay. For polynomial system, one can really take this as the starting point for an algorithmic approach. And this yields what we call Tikhonov-Finichel parameter values. There are three classes of PFPV, Tikhonov-Finichel parameter values for Michaelis-Menten. First one, E0 equals 0. Third one, K2 equals 0. And K1 equals 0 is sort of a half case because K1 and E0 always appear in pairs as a product. How to handle that? Okay, E0 equals 0. All the other parameters positive gives you PFPV. Now look at small perturbations. So take E0 a little away from 0 and see what you get from that. Now, let me get to this timescale approach, which we are going to look at more closely now. So it's about eigenvalue ratios. The Jacobian of that system is easily determined. The characteristic polynomial is also easily determined. Here are the coefficients, by the way. And this is still somewhere in phase space. And then there are real eigenvalues, and these expressions are a little unwieldy, and they're definitely not popular among people more interested in biological matters. So horror radices is the leftover from the Latin I learned in school a long time ago. So what can one do instead? Okay, replace eigenvalue ratios by some estimates. And there is one observation which helps here. When lambda 2 is much smaller than lambda 1, absolute lambda 2 much smaller than absolute lambda 1, and here this much smaller than can actually begin a precise meaning, then the eigenvalue ratio is about sigma 2 by sigma 1 squared. Sigma 2 and sigma 1 are the coefficients in the characteristic polynomial. And then if you're looking at a singular perturbation setting with critical manifold, which I call Y here, define a distinguished parameter basically to be the maximum of those eigenvalue ratios along the critical manifold or along the interesting part of the critical manifold, and epsilon running in some small neighborhood of 0. And this gives an upper estimate for timescale ratios on the slow manifold. So as I said, this is work in progress. So what is the result for Michaelis-Menten here? Let's get back to Michaelis-Menten. That's okay, that's definitely work in progress. First scenario, low enzyme concentration. So E0 is epsilon times some reference value E0 star. The critical manifold is given by C equals 0. And the epsilon star we find just by straightforward finding the maximum and so on is K2, K1 E0 divided by K negative 1 plus K2 squared. This is very close to Reich-Selkov. There's an additional factor K2 divided by K negative 1 plus K2 here, but otherwise it's in the same direction. The second scenario looks a little weirder. So slow formation of product, K2 equals epsilon K2 star. The critical manifold we have seen above. And now the epsilon star, it does have chemical interpretation because here you actually have the geometric mean of two reaction rate ratios. K2 by K1 is 0. Yeah, that's one reaction, well, both reactions going from left to right, so to speak. K2 by K negative 1, that's the ratio of degradation of complex in both directions. So, and this seems to be completely unheard of. So we were surprised by that. And we didn't really want to do Michaelis-Menten when we started that project about timescales and so on. We just thought, okay, let's try with Michaelis-Menten, and okay, turns out that there are some unexpected aspects to that. Now, there is one thing, the small parameter condition we have so far is obtained by timescale estimates near the critical manifold. And one can show, and we have shown, that those local eigenvalue ratio conditions are necessary. The question, of course, is, are they also sufficient? And spoiler, no, not in general. And there are other approaches to finding smallness of parameters and whatever. So an alternative and among specialists quite known approach to small parameters is via Lyapunov functions for the Tikhonov standard form. Tikhonov standard form can always be written like that. So this explicit resolution x2 equals gx1 may be written as a factor here. And then just compute the time derivative of x2 minus gx1 epsilon squared. That's straightforward. And then some estimates, okay, you need to restrict things to a suitable compact set. And given hypothesis for Tikhonov-Fenichel, there is first a positive constant so that the factor A is less or equal than negative gamma. Gamma is positive. And this G prime times F4 tilde, whatever that exactly is less or equal than kappa tilde. And so for V, now that's the, so to speak, the distance, square distance from the point on the trajectory to the slow manifold. For that, one obtains a differential inequality, which looks like that. Okay, there's a differential equation related to that. That's a Bernoulli equation. Just compare with the solution of the Bernoulli equation to get that expression here. V is less or equal to V0, that's negative KT. Then comes here this factor, which is sort of the survivor when T becomes very large, kappa by gamma squared. And remember, here we have the squared distance. So the really controlling thing is now what I call epsilon double hat, kappa by gamma. So, and what does that mean? Following a short initial phase that's controlled by gamma or gamma inverse, one has x2 minus gx1 absolute value less or equal than some factor to say epsilon double hat. And we're getting a reduced equation with an error term in slow time as soon as the trajectory is close to the slow manifold. Okay, just plug in here, but remember the error. So now let's look at Michaelis-Menten with slow product formation again. And that's work in progress. So just compute the epsilon double hat turns out to be looking quite nicely here. This is not dimensionless. If one wants a dimensionless parameter, one needs to normalize. It seems natural to normalize by the initial concentration of enzyme here. We are not in a small enzyme concentration situation, so that's harmless. And then one gets epsilon hat K2 divided by K1 is 0 plus K negative 1. That's also a mean of two reaction rates or ratios, but now the harmonic mean actually. Can one go any further? Yes. Look at the reduced equation with the error term. And remember that one of the figures I showed you some time ago, it's not enough to look just at the phase portrait or just at the trajectories. One also needs to look at the time evolution. So now we have reduced equation with error term, looks like this, and we have this estimate for the error term. And again, one can compare the solution by a differential equation inequality to solution of this here, which is plus 2 epsilon double hat. And we are not really happy with what we have so far here, and we are still working on that. One criterion is, okay, in the limit t to infinity, that means at the stationary point, the difference between the real thing up here and the approximate solution down here should be small. And this would give us the epsilon question mark K2 divided by K1 is 0. But this is very unfinished work. And okay, we hope to get better, and we hope to get a better approach to that, actually. So what's the moral of the tale? First of all, there are various vantage points, various points of view for deriving small parameters in singular perturbation settings. It depends on what conditions you want. Small eigenvalue ratios near the slow manifold, this yields epsilon star. And this, by the way, is computationally by far the most accessible. Good approximation to slow manifold, this is, gave us this epsilon hat. Good approximation by the reduced equation, this gives us this epsilon question mark. And one should note that all approaches provide quantitative estimates. And of course, we are aware that the parameters are not unrelated, but the relation in general is not so easy to tell either. Okay, final comments. I limited things to dimension 2 here, mostly for ease of presentation. But there's a second reason: extension to higher dimensions is possible, but it gets much harder work to get the estimates and so on. And in the given context, we sort of succeeded in giving this enigmatic relation much less than a clear meaning. Now, if you want to have an error of less than 10%, we know how to deal with that, or we know what to require to guarantee that. That's one of the advantages of those epsilon sets and whatever. Okay, so I've more or less stayed within the time limit. Thank you very much.